1,000 years ago. Algebra was created to solve inheritance problems in ancient Persia. Inheritance last wills were often written in a flowery language, stating the relative proportions of different properties that people should get. To ensure that everyone got the right amount, systems of equations had to be solved. Today, we use the same concepts in linear algebra to understand financial markets. Moreover, artificial intelligence is written in the language of algebra, which we will need to master to be able to communicate with computers. In fact, vectors are so important for artificial intelligence that the leading international institution for artificial intelligence is called the Vector Institute and is home to leading experts, including Jeff Hinton, and Raquel Urtasun. We organize data using vectors. A vector is, to begin with, an organized collection of numbers. They could represent the price of 2,000 stocks or the dates between two events. These are examples of what we refer to as structured data. Unstructured data, such as words, images, or videos, can also be represented by vectors, but this is advanced and we will not consider it here for now. For simplicity, in our examples, we would mostly use vectors with 2 or 3 components, but in practice they could have thousands or millions of components. Think of a vector as any column or row in a spreadsheet. Vectors are the fundamental building blocks of linear algebra. Geometrically, a vector can be thought of as an arrow in a coordinate system with a direction and a length rooted at the origin. In the example, we have 2 vectors representing 2 arrows centered at 0 and with directions to the points 3, 4, 3 in the x direction and 4 in the y direction, or 6, 2, which is 6 in the x direction and 2 in the y direction. Mathematically, they are usually represented as a letter with an arrow sign on top. When it is clear that we're dealing with vectors, the arrow sign is often removed. In computer science, a vector is an ordered list of numbers, which happen to be the coordinates of the vector. They can be expressed as columns or row vectors, depending on the context and the convenience. In our case, the first vector could be a column vector, 3, 4, or it could be a row vector, 3, 4. The second vector could be vector 6, 2 as a column or 6, 2 as a row vector. This distinction will be relevant in the matrix section that's coming below. Aside from organizing data, the strongest application of vectors has to do with establishing relationships. Of those, linear relationships are the most common, and spaces of vectors which exhibit natural linear characteristics are important. They are called vector spaces. The basic operations that we need to do involve 2 things: addition and scalar multiplication by a number. Addition of vectors, or expressed as v plus w in this case, with a vector notation on top, is an operation that you do adding the individual coordinates of the vector. Similarly, the multiplication by a scalar, where alpha is a real number, is something that you do also by multiplying each component by the corresponding number. In our example, we can add the two vectors VW by adding their individual components, 9, 6, being the result, and you can multiply it by a number with the resulting vector being the vector 6, 8 column or row, depending on the context. And these considerations lead us to the main objective, which is the properties that vector spaces should have. For a vector space that we call V, and the set of real numbers denoted as usual by the boldface script R, then is a vector space if it has the following properties. On the one hand, when we add vectors, it shouldn't matter in which order we add them. These are one of the things that we take for granted, but it's very important that when we create spaces of vectors, whatever they are, this property has to be maintained. It also should not matter in which order we add vectors. This is what's called the commutative property. Next, there has to be a zero vector. This is a vector that leaves any other vector the same. Again, this could be a vector that we take for granted. We think that this is the vector 0, 0, where all the coordinates are 0. But as we aim to do this in abstract spaces, the existence of such a vector has to be guaranteed by the definition of what a vector space is. Next, for every vector in our space, there has to be a negative of it. There has to be a vector that when we add them together, we get the zero vector. And finally, we want the scalar multiplication to be commutative and distributive. Distributive means that if we multiply the sum of two numbers against a given vector, the result is what we expect, which is the sum of the individual products. And similarly, when we multiply a single number by the sum of two vectors, we expect the resulting vector to be the sum of the individual multiplications. And then finally, the number 1 should leave every vector invariant, the same. When we have all of these properties in a given set, the result is a vector space, a linear vector space that has all of the linear properties that we need the vector space to have so that it's useful for us. Examples. Our first example is one that we know very well because we live in this space, is R3. This is what we normally denote as the Euclidean space in 3 dimensions. This is the space where we live in. The zero vector is obviously the origin, which is represented by the vector that has zeros in every one of their components. Given any vector, there is a negative of it, the sum of which gives us a vector which is at the origin. For example, the vector 3, 2, 1 has a negative, which is minus 3, minus 2, minus 1. The addition of the 2 gives us 0, so it does have that, and all the other properties that we want vector spaces to have can be easily checked. Another example, which is perhaps not as obvious, is the space of all functions. The space of all functions can be denoted by this. These are all the functions that take real values and gives us real values. They map the real line into the real line. For every real number that we give the function, we get back another real number. The set of all these functions is a vector space. In this case, An element of the vector space is not a vector with a finite number of components. This is what's called an infinite dimensional vector space. And its elements are functions. Perhaps not what we think intuitively as a vector in our everyday conversation, but it's a vector space nonetheless because it satisfies all of the properties that we listed above. The zero vector in this case is the function which is equal to 0. But there are many other functions which are here. We have in this diagram examples of functions which could be here. The polynomial x squared minus 1, the function which is x plus 1, or the cosine function which oscillates, goes up and down. All of these are functions, and therefore they are vectors in this vector space. Vector spaces are so useful that they allow us to understand not only geometry, but also they allow us to understand spaces of functions. And spaces of functions can be used for anything. They can be used for face recognition, they can be used for music compression, they can be used for many things. And in fact, when we're dealing with unstructured data sets, vector spaces of infinite dimensions become very useful. Next, we consider subspaces. These are vector spaces which are part of a bigger vector space. So in this case, we can consider a bigger vector space and a subset of that which also has a linear structure. It's also a vector space. So a vector space inside a bigger vector space is called a vector subspace. Because it's part of a bigger vector space, it will be a vector space if certain conditions are met, which are listed here. We need the addition of two of its vectors to always belong to it, and the multiplication of any of its vectors by a number to always belong to it. An example of a subspace is the set of all polynomial functions. This is a subset of the vector space of all functions that we saw before. In this presentation, I will point out that the algebraic problem of doing pattern recognition, music compression, or many of the problems in artificial intelligence is mathematically similar to solving the inheritance problem of ancient Baghdad when the number of heirs is infinite. By the way, the word algorithm comes from the name of Muhammad ibn Musa al-Khwarizmi, the original author of the inheritance problem in the year 850 and the director of the House of Wisdom. His book also introduced the numerals that we use today, which replaced the Roman numerals and signified the beginning of our ability as humans to do complex calculations, which were very difficult with Roman numerals. His book title introduced a new term, algebra, which is where the word algebra is derived from. Turing, 100 years ago, introduced the binary numerals, which is the number system that machines use, and he used them to implement algorithms in a mechanical way, creating the first computer. Therefore, the algorithms we have developed over the last 1,000 years using state-of-the-art hardware have allowed us to reach infinity when compared to ancient Persia. We have come full circle since then.